So the genesis of this is that, as people have said, a draft, two drafts actually, FIPS 203 and God damn it, and hang on, there we go. FIPS 203 and 204 were published by NIST. Those are the two cryptographic public key algorithms that are supposed to be quantum resistant. So when it was published, I implemented them to try to get a better sense of how it would affect confidential computing. So I'll tell you that. Just the quick background, when people talk about cryptography, they're really talking about a suite of algorithms. There's typically a public key algorithm, RSA 1024, 2048. Then about 2002, several algorithms based on elliptic curve cryptography. So RSA is based on integer factorization. That's the hard problem. And ECC is based on discrete log in an elliptic curve. Public key algorithms are used typically for authentication and key encapsulation. So key encapsulation is you want to send somebody a symmetric key, like an AES key, and you encrypt it with their public key so only they get it. Then there's symmetric key algorithms, which are used for bulk encryption. DES was one of the early ones. Then around 2000, there was a new standard AES and came in three flavors, a 128-bit key, 192-bit key, and a 256-bit key. And your intuition should be that a cipher, a good symmetric cipher with a k-bit key should take about 2 to the k operations to break. And then finally, cryptographic hashes, which are used to digest messages. So they're supposed to be able to stick up. As long as a thing you want in, you get a standard size answer, and it should be very hard to get another thing with that answer. It's used for all kinds of things, message digesting, mixing, digital currencies, all sorts of things. And the intuition should be the strength of a cryptographic hash that's well designed should be about 2 to the k over 2, so square root of the corresponding symmetric cipher. So I often, let me close this so I can see my own screen. I often use this slide, yeah, there we go, to describe the confidential computing primitives, isolation, measurement, secrets, and attestation. And I just put a little quick note in here about where things are used. This is not complete. So for example, isolation measurement typically involves hashing something to get storing secrets usually involves a symmetric cipher. And attestation, the thing people talked about earlier, is a public key operation. And I should mention that when we talk about quantum resistance, typically the only thing we really care about is the public key operation. It's not terribly sensitive to symmetric ciphers and hashes, so those are not expected to change. There are other places we use it in confidential computing. For example, typically people will encrypt memory. That's done with a symmetric cipher, but those are the three operations that we'll care about. Oops. Yeah, there we go. As I said, I already said this, RSA, all public key systems are based on a trapdoor or asymmetric encryption. So one side can use a public information to encrypt stuff, but the receiving party uses a private key to decrypt it. And correspondingly, one party signs with a private key and anybody can verify it with a public key. So RSA is based on integer factorization and ECC discrete log. The newer algorithms are based on what is thought to be a quantum resistant hard problem, that is finding the shortest vector in a very high dimensional lattice. And there are two implementations of it. One is called learning with errors, or LWE, and the other is called ring learning with error. About 2002, people started rationalizing these cipher suites. And the idea is you wanted to make the public key operation and the hash operation about as resistant to attack as the public key operation. And to do that, this surprises some people. An ECC 256-bit key is actually equivalent to a 3072-bit RSA key or an AES 128-bit key. And people are surprised when they see what's the equivalent of an AES 256-bit key for RSA. It's actually a 15K key. And this is sort of a downside of RSA. The key size grows quickly with the resistance. That's actually not a feature of ECC. You'll see the ECC keys don't get much bigger, but there you go. In 2017, I'm sorry, this may seem a little US centric, but I think people mostly use the standards. There is a pre-2017 Suite B, it's called in the US, government standard. So if you wanted to sell to the government and you wanted them to use your commercial crypto, you had to implement these algorithms. And they actually had two separate ones. The secret level was RSA 2048, ECC 256, a 256-bit hash, and AES 128. So these are all supposed to be roughly equivalent to 128-bit AES. RSA is not. I actually think I got the top secret one wrong. I think it's 2048. But there's also a top secret one, which RSA 3072, that might have been 2048, ECC 521, SHA-2 512, and AES 256. And then about 2020, the government said, oh, this is too complicated for people. Oh, this is wrong. I'm going to correct this now. This is very bad. Well, sorry, maybe I will correct it now. They said no more secret, top secret, the same level for everything. I think it was RSA 3072 here, ECC 384 and SHA-2 384. And then the symmetric key was AES 256. Again, you may be a little bit shocked about these key sizes. AES 256 is more powerful than, is more resistant than, say, SHA-2, even in a simple calculation, or RSA 2048 by a lot in ECC 3084. But the arguing was, well, people never really implemented AES 192. They did 128 or 256, so why complicate matters? And then recently, the standard has been sort of solidified and it's been renamed. It's called a Cryptographic National Security Algorithms 2.0. And this one I'm pretty sure is right, is RSA 3072, ECC 384, the 34-bit hash, and the AES 256. Okay. So the world was fine up till about, well, crypto has actually been fairly stable for a long time. But in 1994, Peter Shor came along with a new algorithm based on a relatively new computational model called quantum computing. In quantum computing, you don't have bits, you have qubits, which actually have many states at the same time, and even more important, can be entangled. So bits, qubits share a state. And it's actually the only non-Turing computational model. Everything else is sort of equivalent to a Turing machine. And people for a very long time, I should say there are two things. There are two kinds of qubits. I could spend a long time talking about quantum computing, but we're not. There's physical qubits, is sort of the most basic kind of quantum states. They are not very long lasting and are very error prone. So a whole bunch of them are aggregated into something called a logical qubit using quantum error correction. So when somebody talks to you about a qubit machine and they want to brag about how many qubits they have, they will typically talk about physical qubits. And so if you ask them how many logical qubits they have, which is what you need for Shor's algorithm or any other real quantum algorithm, they'll sort of go quiet and maybe say, well, 0 or 1. In 1994, Peter Shor came along and said, we can use something called a quantum Fourier transform to vastly improve the speed of either computing direct log or integer factorization. So in fact, so fast that in the quantum time step, breaking integer factorization in discrete log takes about the same time as actually doing the encryption. That's bad for a public key system. Now, for the skeptics, I should point out there is no quantum computer in sight. There is a National Academy of Sciences report, Quantum Computing Progress and Prospects, in 2018 that sort of looks at where people are on the scale of building a quantum computer with a decent number of logical qubits, and it's not horribly encouraging. Okay, but despite that, NIST said, okay, there's an algorithm, at least a theoretical algorithm, that would break our current public key systems, and we better start having one that's rooted in a quantum hard safe problem. And again, there are several candidates for it, I'd say, but typically what people focused on is the shortest vector in a high dimensional lattice, or SVP problem. It has very nice provable properties. In the very early days in cryptography, people offered public key proposals which had good worst case hardness, but most of the time it was easy to break. So that's not very good. The quantum safe algorithms that have been proposed not only have pretty much average worst case hardness, they've been designed to be resistant and shown to be resistant to sort of very high class attacks, chosen ciphertext adaptive attacks. There are two classes of implementation. I should say NIST announced the intention of having public key systems based on different kinds of algorithms. Another one is called the McLeese system, based on coding theory. But I expect everybody will use the shortest vector algorithm things. For one reason, McLeese, for example, has a gigantic key size. And there has been haven't not seen a draft standard on anything but these shortest vector and lattice-based things. So there's learning with errors, and basically the problem is solving simultaneous equations over finite fields and deliberately introducing errors. And the trapdoor is, if you know a particular representation, you can round out the errors, get rid of them. Frodo was based on learning with error. I'm sorry, learning with error. That's called learning with errors. Then the downside of that is those systems have very large keys, and to address that, people started using ring learning with errors. It's roughly the same, solving simultaneous equations over finite fields, but this time over a ring, like the integers mod p, adjoin x. This may mean nothing to you, don't worry too much. Mod x to the n plus 1, and n is about 256. So that's the standard. The winner, the thing that caught my attention and made me start implementing, was published in April. And here's the first wrinkle. The public key shortest key standard is actually two standards. There's crystal dilithium for signing and authentication, and crystal kyber for key encapsulation. Previously, all the other public key systems, signing and key encapsulation, were roughly the same. They weren't really different algorithms. Both of these standards is based on ring learning with error, that hard problem, but they're a little bit different. Actually, they do use different primes. You'll see how they're different. And as I said, they have some nice properties, including shortened key sizes and provable properties about attack. Chris Pikert and Oded Regev are typically the names associated with proving these things. So at this point, I'm going to talk for about 4 slides, and you should go into Zen mode, because there's no way on earth you can understand all this stuff if you haven't seen it before in the first glance, but it'll give you a sense of what people are talking about. I've used the word lattice a lot. Lattice is really just not a vector space, because vectors over field, is a module, I guess is the right term. And instead of having a field like the real numbers, it's over the integers. N is the dimension of the lattice, and they're typically linearly independent. And I've defined the colattice here. The CVP, which is the only thing you should focus on here, the problem stated succinctly is find the vector in that lattice, the thing generated by that thing, which has the shortest size. LWE is based on finding noisy linear equations, mod q, mod an integer. And just as a forecast, the two primes used are like around 8 million. It's actually 2 to the 23 minus 2 to the 13 plus 1 for dilithium, and 3329, which is easier to remember for Kuiper. So you give a bunch of equations, more than the number of variables you're trying to solve for, and you add some error to that. And the errors are chosen from a distribution of errors. Typically not exactly the binomial distribution. It's normally some Gaussian-like distribution. And the decision problem is here you're given B is to find S, a secret S, knowing AS plus E, where A is a matrix over that thing, given the fact that A was chosen randomly over that field. And it's hard to do that. That's a hard problem. Again, just quickly, a typical learning with error problem looks like this. You choose a random distribution for three sets of matrices. One is a secret matrix, one is a public matrix, one is an error matrix. The private key is that first public matrix, and then AS, which is the secret key, plus E. E is the other vector. To encrypt, you choose a vector uniformly at random, and you compute this thing. And then to decrypt, so the ciphertext consists of two things: U, which is A transpose A, and C, which is P transpose A plus this thing. It's the rounding thing. And when you decrypt, you subtract STU, the secret matrix. That will give a matrix which is close to the right answer. And then when you round, you'll get the actual right answer of zeros and ones. Learning with error and ring learning in principle has a probability of failing, so you might have to try it twice because of this rounding operation. But in practice, it basically always works. Just to be a little bit more concrete, here's an example. Here's the randomly generated matrix over a field over where Q is 23, which is in fact a prime. And the distribution is a Gaussian distribution with that standard deviation. So there's the public matrix, there's a secret matrix, here's an error matrix, here's the computed P. And to encrypt, I give an example of encryption using those exact same matrices. That's it. Now, the downside of this is look at the size of the keys. Here you have A, and we have a tiny Q. Typically, Q would be very large. As I said, in something like crystals, it's like 8 million. And I have a 4 by 1, 2, 3, 4, 5, 6, 7. That's not right. 8, a 4 by 8 matrix, 32 of these. That's the first part of the public key, and the secret key is equally large. So these key sizes are quite large compared to, say, RSA. Ring RSA uses the same idea, but as I said, the computations are done not over the integers mod prime, but over this. And again, I apologize if you've never used, you're unaccustomed to finite fields and modules. This may look like gobbledygook, but it's you take the polynomials with coefficients from the integers mod q to infinitely long polynomial, and you reduce by a single polynomial x to the n plus 1. That's the basic computation. That's the ring we do computations over. And don't worry about this other stuff, but the ring LWE problem is at least as hard as solving the closest vector problem. That's the thing Pikert and Regev showed. And the advantage of ring LWE systems is the key sizes are smaller. Okay, so now let's get to the winners. The two winners were crystal dilithium. I don't know where crystals came from, the word, but I know where dilithium and kyber came from, or dilithium and kyber. Dilithium is the signing algorithm. Kyber is the key encapsulation algorithm. In both cases, they use this ring learning with error, and the ring is Z mod prime. But the prime is a rememberable 3329 for kyber and a rather enormous, about 8 million something for dilithium. So the key takeaway is when you do these either encryption or signing or decryption or verification, all the operations look like familiar things. They're modular arithmetic that we all grew up with, like you use in ECC. At this point, I'm going to say something, and if you don't understand it, just let it go. There's a particular reason they chose n equal 256, and that's because this ring has primitive 512 roots of unity over that. And as a result, they can use a trick called the number theory transform to turn convolutions, multiplications which take n squared time, into pointwise multiplications which take roughly n time. So that's the only spiffy thing in it. I'm going to give you a very quick simplified dilithium, and then as I just did, I'm going to race through still simplified, but closer to the actual implementation one. And I'll do a race through of the kyber because I really want to get to the effects. So for dilithium, A is a K by L matrix with entries over this ring I just told you about. So the ring itself, the entries are pretty large. You've generated two secret vectors, one of dimension L called S from this ring. And it has random coefficients, but they're always less than or equal to n, eta, sorry, in size. And then another vector S2 of dimension K. And you compute, part of the public key is this computed AS1 plus S2. The secret key is S1, S2. The public key is T and A. Okay. So to sign something, you generate a random number a random entry in this ring where all the coefficients have size less than gamma 1 minus 1. Gamma 1 is a parameter of the algorithm, and you'll see that in a minute. You take the high bits of, you take this matrix A, multiply it by this Y, random Y you just generated, and take the high bits. Never mind how you do that exactly, but it's high order bits. You take that number you just generated and you take the message you want to sign, append this W1, and do a special kind of hash. It's actually SHAKE256. And then you compute Y plus this hash thing times S1. The signature consists of Z and C. To verify, you compute the high bits of AZ minus CT. And when you compute that, you'll see that it's the same thing you expected before, you got before when you signed, but you didn't have to know S1 or S2. You compute that special hash again, and you make sure the two hashes match. There's another condition. You want to make sure that the coefficients in Z are not, that thing, absolute value Z infinity just means the maximum of the coefficients, yeah, and the polynomial representation in the ring R. That's a little bit of a sideshow. Don't worry too much about that. In the real implementation of dilithium, the prime is this thing, 38,380,417. The ring is Z sub that P mod 256 plus 1. K is 1, L is 4. Those are the dimensions of that matrix. Gamma 1 is P minus 1 over 16, blah, blah, blah. You can see all these things. But the basic idea is the same. When you do keygen, you generate a matrix over this ring. And this is just a regular old random distribution. The secret key you generate from the same ring, but you make sure the coefficients of S1 and S2, which are both vectors, are less than or equal to eta. Eta is one of the parameters of this It's like, and I've given you the parameters for the strong version of dilithium, by the way. The public key is AT, and the private key is S1, S2. One of the reasons the key sizes are smaller is that A is generated actually from a seed in SHA-256 rather than specifying it by specifying each entry. That's sort of the trick used. I'm not going to go through this in detail. This is very much like what I just said to you about how you compute the signature and the verification of the signature. So that's dilithium. I actually, despite the fact that you might have think I've gone crazy, I actually simplified it again quite a bit. There's additional stuff in the, it actually took me about 2 weeks to implement these two. And there's lots of bells and whistles in the real implementation. They use hints about the sizes of things, all sorts of stuff, but I wanted to simplify it so you got the basic idea. Kyber is very similar, but the prime is much smaller. And I introduced this number theory transformation that makes multiplication easier. So again, very much like dilithium, you compute you generate the A, although A is generated from a seed, which is why it's compressed. You compute this secret, AS plus E, but you actually do it in the transform domain, which makes arithmetic faster. You generate random noise. Again, forget about CDB A-1. It's just a way to generate elements of this ring which have coefficients of size less than or equal to A-1, and an error generated from something like that with an error less than or equal to A-2. You compute this number. Decompress and decode are ways to squeeze and expand numbers. And again, the encrypted version of that is these two things you've just computed. To decrypt, you do very much what you did in dilithium. However, in Kyber, there's an extra step. Once you use that, that's a basic encryption algorithm that you use for the key in encapsulation. The key size is actually fairly specifically stated as a 32-bit, 256-bit value, which is convenient since we're going to use AES 256. And I'm not going to go through the details of this. It's very similar. It's more stuff. Okay, so now the punchline. So what's the effect on confidential computing? So the biggest effect has to do with the public key sizes. For example, old SGX, the first one, used ECC 256, which was the secret standard at the time when they first did it. AMD SCV uses RSA 4096, which actually beats the latest government standard in the current things. The computation, I showed you all the computations, although your head may be spinning. The compute time is roughly similar. It's more, but roughly similar to the old public keys. And the key sizes are about 1.5 kilobytes. So they're bigger by a factor of 3 or 4, but not crazy big. Okay, so what about the software? How would this change the software used in confidential computers? Well, if you use a framework like the certifier framework in the CCC, the only change is you say, well, instead of using, when you declare the cipher suite you want to use, instead of saying RSA 2048, AES 256, SHA-512, or whatever, you add the new cipher suite, say I'm going to use that, and you don't know anything else. Everything else gets done behind your back. OpenSSL handles all the new algorithms, does the TLS exchange. You're all done. You're all set. Now, if you want to use these keys yourself or quantum resistant keys yourself, then you have to call OpenSSL using these new algorithms, just as you would have called OpenSSL with the old algorithms pre this. The hardware is a different story. So it's very easy to adapt the software to this. It's harder to adapt the hardware to this because you have to implement these algorithms in hardware. They're not onerous. They're actually designed so they could be implemented in hardware without going too crazy. The storage sizes are reasonable. You only need standard machine instructions that, modular arithmetic, and the compute requirements are reasonable. Having said that, I know there are people who from hardware companies on this call. I don't expect people to actually implement the new algorithms in hardware for at least a couple of generations. Nobody's feeling a lot of pressure to do this quickly. Oops, that's it. So, I've done like 20 slides, probably making your mind spin a little bit about these new algorithms. And the bottom line is the effect in the actual implementation, if you use a framework in software, writing programs, is going to be pretty small. In hardware, it's going to be a significant new investment in developing the hardware, and that will take a while. And the key sizes will be bigger. So it's I guess that's the bottom line if you're buying this. So with that, I should have said in the beginning, ask all the questions you want. I typically don't open the chat, but if you have any questions, go right ahead and ask now.
I got a bunch of them, so I'll kind of let kind of up front, I guess. So the first one is when you say hardware, how much of it could be in firmware? The second one
most of it could be in firmware. For example, I think
Okay.
AMD actually has a small ARM core where they do their public key operation, and there's no reason you can't have a small ARM core. You might need a little bit more memory than you used to, but yes, it could be firm. You're going to implement this in firmware. You're not going to. I can't
Okay,
think.
well,
Yeah.
that clearly helps, right? Because
Yeah.
firmware is basically software. But okay, so that's helpful. Two is how do we have a winner yet in the NIST competition, or is that still ongoing? I've lost track.
These are the two winners. This is the winner. I'm sorry. There may be new additional winners that use different kinds of algorithms, not ring learning with error, but this is it. The two algorithms I described, the thing that got me off my ass to implement them is that these are the ones.
The competition did close. I lost track. Okay, that's really helpful.
Yeah, it's hard.
Last one
Well, it's only April that was announced, so you're not way out of date.
Yeah, so the last one is kind of a combination of questions. First is, how confident are we that these actually are kind of difficult to break? And combined with the other question, do you want to give some background into some of the failed ones as a possible cautionary tale?
Yeah. So these competitions since 2000, there haven't been a lot of terrible failures. Like in AES,
Well, there was one that fell in an hour and a half on a laptop, right? That's kind of pretty
for this
bad
new one,
failure.
yeah, there's one called
Yeah.
Psych in the new one that failed. I think that's the one you're talking about. And it was actually sort of a weird implementation side channel thing. So that was really the only failed, like out and out, laugh hard failure that I know of for the new competition. And as I said, even in the older competitions for AES, there weren't like terrible, giggle kind of failures. There were mistakes and stuff, and there are things that, in the crypto world, if you have a 256-bit symmetric algorithm and you find a shortcut that lets you solve it in 2 to 252 operation, it's like big failure. So,
yeah. Well, what I was kind of what I was kind of leaning towards was, the mathematics behind RSA and ECDC are old and well known. The latter stuff is relatively new, and what's more, because we don't have quantum computers yet. What is the confidence? And I've heard it's not as high as we'd like. Wait. The confidence that these algorithms will be truly quantum resistant.
Yeah, I think, well, so there are proofs about there is a quantum model of computation where you can prove that these algorithms are strong based on some assumptions about the computation. They've been around long enough. Ring learning with error have been around long enough, so people have tried attacks. Entru, I don't know if any of you go to the crypto, but even 20 years ago, Entru, which is a ring learning with error based algorithm, there are attacks on that, but I think people have a fair amount of confidence that these will work. The one sort of like inside pool thing of these is one of the submissions was Frodo from Microsoft and others. And what they said is, this ring learning with error, we don't have as much experience as we have with learning in error. So we're going to dump that and we're going to go with the longer key sizes. There may still be a little hesitation about that. But my expectation is you would be like extraordinarily surprised to see someone break these algorithms at this point. So I think they're
Okay,
pretty,
that's helpful. Thank
they've
you.
been well studied. And these days there's actually a formal model for the attacks and the quantum resistance. So people have pre-worried about that. Looks like who's something.
Yeah.
I have two quick questions. So, first, if this is official, then does that mean that if we submit like a FIPS certification request, then they will formally be FIPS certified? Is that?
It will be certified. So the algorithms themselves are now basically formally certified. That's what the FIPS publications are. But the hard work in crypto is actually the protocols that use them. And so now the standardization in things like TLS, IPsec, every other protocol has to go through that. That is not done yet, as far as I know. So that's work to be done. So you know, you don't have to run to your terminal and implement these right away. But it started, and you know, the first step is specifying the algorithms, and they've done that.
Gotcha. So if I directly call these signing and encryption operations, those would be considered FIPS certified, right? But if it's larger, okay.
Yeah, you guys know the standards business better than I. It's called a draft publication now, but at this stage, this is it. This is really the standard.
Cool, thank you. Another question is about optimization. Like, do you see, you know, you can optimize with the existing hardware instructions, like matrix acceleration?
That's a good question, and it goes to Mike's first question. Some of the other algorithms, people have added special hardware to accelerate them. Not a public key, but as an example, might have been AES. You might remember Intel added some special instructions to speed that up. And for ECC, there are some computations, they added some special instructions. I don't really know of any special instructions I'd add for this. If you can do modular arithmetic fast, that was the whole reason for implementing it. I wanted to see if you can do modular arithmetic fast, you're in pretty good shape. I don't know, they've done this number theory transform, which is certainly an optimization, but you don't need to do anything special in hardware for that. So I actually don't know of any like super duper hardware, you know, based thing you'd want to do to speed up these algorithms.
John, one exception to that, I think, is the shake hash itself, which is, you know, something that, you know, the SHA-3, the Ketshake primitive in that was designed to be very efficient in hardware, and it on general purpose instruction sets, it doesn't perform particularly well in software. So that's one area that I think. I'm
talking about the algorithm itself, not the algorithm it uses, which you're right, is basically a SHA-3 derivative.
In my work, I've seen greater than 50% of the compute cycles in Kyber and dilithium are spent in shake.
Yeah, that sounds right.
Hugo, given that you're looking at this, are you able to make comments about the assumption, well, the statement John made about the likelihood that a lot of this could be happening in firmware?
I agree with John on that. Yeah, I think if you look at what computer architectures have done for RSA and ECC, the answer is not much, right? It's basically just software in 99% of cases. There's exceptions around side channel resistant implementations and stuff like that, but I think generally you'll see this being deployed in software and in firmware, including in, you know, secure enclaves and hardware security subsystems and so forth.
Yeah, I should say when I implemented these, I didn't pay so much attention to side channels. I wanted to understand stuff, but the protection you would employ against side channels is very similar to the stuff that's been developed for like ECC or something.
Hey, John.
Oh, it's Chris.
Hey, good morning. Hey, you ran a panel with the National Academy of Cybersecurity Forum, where there was a lot of discussion about the idea that these new key exchange mechanisms had potentially different protocols.
Oh, they will have different protocols, somewhat different.
And so is that relevant in the context of confidential computing? And if so, how?
Well, again, I'll be a little bit monomaniacal here. The only algorithm we care about in the certifier framework is TLS, and that's been worked out. So I'm not worried about that at all. The protocols do have to be specified. I don't know enough to know that in some cases, it won't be more work than people expect. But for confidential computing, as far as I can tell, for the protocols people actually care about, I don't think there will be a whole lot of a problem.
Super, thanks.
I have a question that goes a little bit beyond the current run of the standardization. So it seems like we start to have an idea on the Shor's algorithm part on the public key crypto. Can you comment a little bit on if there's anything on the horizon for like Grover's algorithm for AES like AES follow-ups? Do we need those in the next 5 years, 10 years, or is it not necessary at all? Or can you?
Yes, I will say something about that. So Grover-Ritz algorithm, the thing he points out is a square root improvement for search. And you might think that's a big deal. So you'd have to double the key sizes. So, okay, right off the top of your head, you'd say, okay, well, if I use AES 512 instead of AES 256, I have the same protection. But the thing about quantum computing is it's very hard to get information into a quantum computer. They're very fast for computing, but they're not so great at I/O. So Grover's algorithm is not really a practical attack right now against an asymmetric system or hash-based system. And don't forget, Grover's square root improvement, the quantum, Pete Shor's algorithm is an exponential improvement. That's a big frickin' deal. I think it's a good thought to worry about Grover, but right now, as a practical matter, putting lots of large numbers into a quantum computer doesn't seem like, even if you had a quantum computer, it doesn't seem like a terribly easy thing to do.
There's an additional point there, which is for implementing Grover on, quantum computers we can imagine in the foreseeable future, it requires a great deal of memory, and
right.
that the square root speed up assumes you have infinite memory, let's say, or a very large amount of memory, and foreseeable quantum computers will not have that, and so practical implementations of Grovers will be significantly slower than that theoretical speed up because they have to make space speed trade-offs.
Yeah, I agree with that. So the bottom line is, the simple version of this is worry about the public key systems. Don't worry about anything else.
Yeah, of course. But but you're also then saying that, like, you don't even see like in 5 to 10 years, it's opening up another. So we're actually good for now.
Yeah.
Perfect.
Public key.
Thanks.
I'm sorry, who is the guy who helped answer that question? I agree with that. I've forgotten his name now.
I think that was me, Hugo.
That was you, Hugo. Yeah.
So John, I would love to hear a little bit more about the certifier framework aspect of this. When Aditya suggested this, I got the sense, but maybe incorrectly, that you had integrated some of this.
No, I haven't. Yeah, and I'll tell you why. Only the reason to do the integration, which we will do, has to do with hardware. I mean, if you have hardware with a susceptible algorithm, it doesn't make a whole lot of sense to make the software much stronger. So really, the earliest you care about this is when the hardware is available. The thing about the certifier, though, is that if you were a programmer, remember the whole idea with certifiers, make it as simple as writing hello world using confidential computing. So the nice thing about the certifier is when you use this, it's almost transparent. There's one declaration you use that says, I want to use this public key system, not the old ones. And then all the computations happen behind your back. And the only other time you have to worry about it in software is if you want to physically use these keys yourself. Like, here's a key I got in my hand. I want to actually do a Kyber or dilithium, yeah. But so I don't think there's a huge hurry, and I think the gating factor. I do some hardware, but my guess is if I hear an announcement about new hardware for confidential computing that uses this, I'd be ready to implement the software part in a big hurry.
Okay, and then you commented a bit ago that the certifier framework only cares about TLS. Does it also care about signatures?
Well, signatures are used in TLS and certificates and all that stuff, but TLS is the only protocol that requires standardization that we use. And in fact, we could do it without a standardization of the protocol. But it'd be nice if that my answer is you don't have to change anything except this declaration applies as if TLS has a well accepted protocol for doing the things it does now using these new public key systems.
Okay, and I guess I was thinking of signatures in terms of attestations. Maybe attestations are intrinsic for you.
That's right. When you check these attestations, you'll check the signature using dilithium. But again, the framework does all that for you. So, or in fact, OpenSSL will do that for you. So it's like, okay.
Okay. And then last thought about implications for software is the key sizes you mentioned. So we think a lot about like the computational complexity differences, but what about bandwidth increases, message size increases?
There are two answers to that. The first answer is, well, 1.5 is not so much bigger than 0.5 with comparative key sizes. The longer answer is, people often have embedded keys in places where for some reason, this certainly happened with RSA, is, when people switch from 1024-bit RSA to 48-bit, it took them several releases because it turns out they allocated space for only 1024 bits and took god awful long time to make that bigger. The in principle answer is they're not so big it should be a problem. In practice answer depends on the particular implementations. As I said, for standard protocols using Agile crypto, it shouldn't matter at all. But I am not saying some crazy IoT guy did something wacky in, somewhere and assume the key size is only something and, now he's got a problem.
Okay, good answer. Thanks. It's like Chris is next.
Looks like I'm up again. So John, Manu raised a comment in the chat about hybrid techniques, and wondered if you can first of all sort of update what is the status of that discussion, because I know some people were opposed to using
I don't think that
mode.
discussion will, let me say a little bit more. So people are suggesting that people use the quantum resistant algorithm and an older algorithm instead of just a single one, sort of just roughly think about encrypting twice. And I don't know exactly what people are worried about. I suspect, my guess, having done this at Microsoft, is if you tell people you're going to take twice as long to do a public key operation, they go ape shit and don't want to do it. So my guess is, at least for authentication, people won't do it. Maybe for key encapsulation, they will. But it's, it's the how many suspenders you want versus how much real time you're going to spend computing. I can't answer that question. I don't expect the argument to ever end. Well, the only thing that will happen is, 10 years from now, we'll count the number of guys who did the double encryption stuff, the hybrid, and count the number of guys who said it wasn't worth it. And that'll be the answer. It's kind of more like a vote thing than a theory thing.
Got it. Thanks.
Am I up, Dan?
Yeah, sorry, I didn't lower my hand.
Yeah, no. Sorry to keep coming in, John. So one thing that I've heard talked about, and I'd love to have thoughts of you and anyone else on the call, particularly from the hardware vendors, silicon vendors, is implementation of quantum resistant algorithms within TEs. Are there any things to be careful about, anything to worry about, any again speed up? So I mean, we all know that you can write an application in a TE which is terribly slow if you put your mind to it. Is there anything to avoid, and any shortcuts to be thinking about when you're doing implementations in TEE?
Yeah, I don't think much. Don't forget, what you really do is call OpenSSL when you use these things. Assuming
well, no, I'm really talking about not doing that, and talking about people who are actually writing implementations specifically to be run in, which are optimized for that use case, rather than taking an OpenSSL.
There's only a general answer. Be careful with side channels and a lot of stuff. Do it right. The normal advice we give people in crypto is, for Christ's sakes, don't implement your own algorithms. You'll screw it up.
Well, indeed. Yeah, no, I know. But I do know one or two people, and I literally know one or two people who I would trust to do this. And the question is coming up, and I think it's a good question to ask.
Yeah. Hugo, actually, I should point this out, says that Meta, AWS, and Google have already implemented hybrid implementations. I'd say that's fine. I expect that. I expect everybody to implement them. I don't expect everybody to use them all the time in day-to-day business. Although maybe by the time this happens, computers will be so fast we won't even notice anything. But
well, they'll all be in our heads within the next 10 years, right? We'll just be on the grid or in the matrix or something. Thanks, John.
Okay. Well, I hope that was fun. I'm sorry, I ran through the mathematical details, which I find very interesting, but that's like you have to take a 3-week course at least before you can do that, and it was a shorter talk. So
but this is a recorded talk, right? Which means that people can go back to it, which is really useful and really fantastic. So thank you so much for doing that, John. It really is beneficial and useful. Thank you.
Great.
And in fact, one of the things that we're trying to make sure that we do more of is blog posts. It's just another way to to share the information for people who aren't going to watch a recording. So if you'd be open to it, it would be great to get a short blog post from you on your thoughts.
Yeah, and I think that the tagline for the blog post is really, these standards are now announced. You should be ready to use them, because when the hardware comes along, you want to use them. I can talk about some of the details about key. I mean, I'm not going to go into as much detail as I did here, but I can talk about key sizes and all that stuff.
Yeah, I think even just a couple paragraphs. I mean, maybe that's too short, but a lot of times I think people shy away from doing the blog post because I think they're writing a big article, but giving people just snack-sized information is also really helpful.
Yep.
I know I've heard from the board, from at least one board member, that they really wanted to hear from Attack about post-quantum stuff. So I'm going to point them at this recording, but yeah, a blog would be great.
Yeah, again, the one thing I'd emphasize is, it's not clear how crazy you should go about post-quantum until the hardware is there. If you're really worried about a quantum attack, then the hardware has to be quantum resistant too.
Yeah. But I think that's all good context to explain in the article.
I mean, a great quote, a great title for, or a subtitle for a blog post is "Don't forget to wait for the hardware," or
But Mike, you called out the absence of this kind of capability in your gaps list. And indeed, there are use cases that are going to involve long-lived data. And so it is important for the hardware to start working on this, the hardware teams to start working on this stuff.
Oh, 100%. And the fact that we have people here from Intel and any AMD folks here, we may and NVIDIA.
There was an ARM person. I'm sorry, there was an AMD person.
Suggest that people are paying attention, and I think it's something that I kind of mentioned to folks, in my role as the ED from time to time when I meet them, to just keep nudging. I'm sure people are aware of this. I'm not expecting anyone to be making announcements in the CCC TAC meeting. I would advise against it, making hardware announcements. But you're quite right. We do need to be chivying people along and making it clear that if you care about this stuff, this is an important place to be putting it.
Yeah, and I think the vendors have already done. For example, I mentioned AMD uses a 4096-bit key, which is already a little bit of protection. So.
Okay, great. Well, thanks again for the talk, John. Thanks everybody for the good questions.
Hugo, thanks for helping. Maybe you want to co-author the blog post.
Yeah, we can certainly talk about that. Yeah, I'd be happy to do that.
Okay.
Are you in
That'd be
Cambridge,
wonderful.
Hugo? You elsewhere?
I'm in Cambridge. Yeah.
If you ever
Yeah.
fancy a trip to the Wrestlers, I'm only the other side of Haverhill, so just shout. It'd be great to go.
Oh, great. Okay. Thanks.
My wife and I often go on vacation in Cambridge. We haven't since the what do you call it, the pandemic, but maybe this is worth the trip now.
And get Hugo to take you to the Wrestlers. It's a very good pub with excellent Thai food and very good beer. So.
Okay. Great. Thanks, everyone. I hope it was worthwhile.
It really was great. Thank you.
Thanks, John. It was great.